Hi everybody, I would like to tell you about the example related to shear force diagram or bending moment diagram. Our goal is to find the maximum bending moment in the related beam element or some other components on the structure or machine body. Why maximum bending moment is very important? Because we want to know the maximum stress inside the beam. When you know the maximum value of the inside stress, then we can find appropriate size of the beam. That's our goal of design for our beam element or some other component related to structure. Okay, anyway, in this figure, in this example, I would like to tell you about bending moment diagram or shear force diagram. Firstly, we must think about the reactional value, RB or MB. Okay, in order to find that, we can calculate force equilibrium. Upward direction is positive, then we can say P1 is minus value and P2 plus RB equals 0. Then we can say RB equals P1 plus P2. RB equals P1 plus P2. Okay, next we can say this one is positive, then moment about B point equals 0, then MB, firstly this one, and minus P2 distance, this distance is B, not minus, is positive because this direction, counterclockwise direction, is positive, and P1, and this distance is L, or L equals A plus B. Okay, then we can say MB value equals what? Minus P1 L minus P2 B. P1 L, P2 B. Okay, that's the MB direction. And we found RB and MB. Next stage, we would like to know what's happening in this region, in this scope. A2, this here, what's happening there? When this value x is located 0 to A in this region, A. Then we can draw free body diagram. When you cut there, when I draw free body diagram is like this one. Let's say this one is P1. Let's give like this one. Okay, let's say this distance is x. And we would like to draw downward direction is positive. This direction is positive. Let's say this one is V, this one is M. Okay, we have some kind of agreement related to sign convention. When you think about this kind of beam, when you cut there, then on the right side, downward direction is positive, and counterclockwise direction is positive in the case of moment. When you think about left side is different. Upward and clockwise direction is positive. Anyway, when you think about this one, left side is like this one, right side is like this one. In the case of bending moment, in the case of bending moment, this direction is positive. That's the agreement for nice expression related to bending moment diagram or shear force diagram. Okay, we have this kind of one. When X is located in this area, in this region, X equals in this region, then we can say, you can draw this kind of free body diagram. Okay, then firstly, force equilibrium. And you think about this one is positive, force equals 0, and in this case minus P1 and minus V. Then V equals what? V equals what? Minus P1. V equals minus P1. Okay, next. When you think about moment. This direction is positive. Moment M equals 0. Then M, and this V equals 0. P1x, and direction is positive. That's why M equals what? Minus P1x. M equals minus P1x. The first one. Okay. We found the value, shear force, and bending moment. Okay. Next, let's consider X is located somewhere between A to L in this one. When free body diagram is considered like this one, slightly longer, and distance, let's say X, and here P1, and somewhere here P2. Of course, this distance is A. Okay. Then also we can consider V value and moment M is considered like this one. Okay, then when you consider force equilibrium F equals 0, then let's say upward direction is positive, this one minus V and minus P2 minus P1. Then V equals what? V equals minus P1 minus P2 minus P2. And next, let's think about moment. Moment equals 0. Consider about this one. M is positive, and P1, let's consider this one, P1x plus P1, P2, this distance, x minus a. Then moment, finally, moment is considered with this expression, minus P1x and minus P2 x minus a. Okay. We've calculated shear force and bending moment in this case. Okay, let's draw shear force and bending moment diagram. Okay, in this range, this location A is located there, and in this region, minus shear force diagram, minus P1 is like this one, minus P1, say minus P1. And in this case, minus P1 minus P2. Okay, minus P1 minus P2. Okay, we can draw this kind of shear force diagram. When you have minus P1 concentrated load, we have constant 1. Some change was happened at this point, then we have the constant. If it is integrated, then we can have this kind of relationship. Next, let's think about bending moment. Okay, let's say bending moment diagram. On the left side, in this area, okay, m equals minus p1x, okay, then something is located like this one. And the next one, we apply this one. When x equals a, minus pa, maybe this one, this point. And next, when x equals increased, linearly decreased, then we can have this kind of relationship. Then we can finally have this kind of bending moment diagram. When you watch this kind of bending moment diagram, then maximum value happened at this point. We can find this value when we substitute here, instead of x equals L, then we can find this value. This one is maximum bending moment. In next chapter, when we consider about inside stress in the beam, then it plays very important role to fix the related value. Anyway, when you consider about bending moment diagram, this point is maximum. Or when you compare both of them, shear force diagram and bending moment diagram, if it is constant, if it is integrated, then you can have linear relationship like this one. Here as well, same relationship, same consideration can be applied there. Or we have linear relationship here, and if you take derivative, then you can have this kind of value in this range as well, or this kind of relationship is available. Mathematically, it's also possible. When you take integral once and twice, then you can have shear force diagram and bending moment diagram as well. Okay, that's for finding shear force diagram and bending moment diagram in this case. I would like to summarize this example again. This example is related to cantilever beam. In the cantilever beam, we have two values. First one, concentrated force like this one, and it is supported here. In order to find bending moment and shear force diagram, firstly calculate reactional value, force and moment. In order to find that, applying the relationship like this one, force and moment relationship. Then we can find bending moment and reactional force. Next important thing is separate different range or area, and next this kind of free body diagram. Based on free body diagram, we can calculate shear force and bending moment. Draw free body diagram and calculate shear force and bending moment. When you find both of them, then just draw everything. That's the shear force diagram and bending moment diagram for this example. Okay, now let's consider another example. In this example, we deal with very special type related to beam. When you think about this beam, in the middle we have rotational free and movement free. Movement is fixed, but rotation is free. And some roller moving direction in horizontal direction is free. Of course, the rotation is also free. And we have some special equipment. At this point, we have the shear is free. What does that mean? At this point, shear force is not transmitted to another component, vice versa. And dimension is given for 8 meters. And we have some distributed load here. When you think about distributed load, 1 kilonewton, Q equals 1 kilonewton per meter. When you consider this kind of concentrated force, distributed force, then the force is divided by meter. Okay. In this case, we would like to find the shear force diagram and bending moment diagram. In order to find that, first those diagrams, firstly we must find reactional value. Reactions. Okay, reaction is at this point RA is like this one, and RB, RC. Sorry. Let's think about step by step. When you consider RA value on the left side, in this case, here shear force is free. That's why the Q is distributed load, and the distributed is load length is 4 meters. That's why total Q concentrated force, equivalent concentrated force is 4 kilonewton. Okay, this one is acting in the middle, we can assume. Then reaction is 4 kilonewton. Okay, that's it. And next stage, here shear is free. That's why it's independent one we can consider. In this case, when you think about this kind of direction is positive, then moment is considered. Then MO is given like this one, positive, minus RB is multiplied 8. RA is also positive direction in this case. RA is 8. Okay. Then we have one relationship, and another one is this kind of positive direction is considered. Of course, this one is 0. Considered RA plus RB equals 0. RA plus RB equals 0. Based on both relationships, we can calculate RA value and RB. RA value and no, sorry, this one is not RA. RB, RC. I think this one, RC. Instead of RA, this one is RC. Sorry. We can calculate RB and RC value like this one. Okay, we found RA, RB, RC. And next one, we can consider shear force. On the left side, to draw free body diagram is like this one. free body diagram is like this one, and here RA value, and downward direction V, and this direction is positive M. Okay, V equals what? RA value. M equals what? RA is multiplied by, let's say this one is X. If you like another direction, then you can put minus value like this one. Okay. Here something missed. We must consider here in the distributed root. I missed this one. Then equivalent force is what? This force is what? Q is multiplied by X. And then when you consider this one, then V equals what? Minus Q X. Then here positive 1, Qx is multiplied by Q x over Q, x over 2, this distance, half. This distance should be considered. We have some linear relationship, and next one, some second order relationship we have. Next, let's consider this side. When I draw a free body diagram, in this case, at this point shear force is free, that's why we can separate each other. Then let's say Alp, and let's say this distance is X. Okay, then this kind of one, V and M is considered. Then V equals what? Alp. M equals what? Minus M equals plus Alp X. In this case, just consider this range. When x is 0 to 8, when we consider 8 to 16, in this range, the shear free body diagram is different. Alp, and here somewhere this moment MO is happening, and this direction and this kind of V and M is available. When you consider it, then V equals what? V equals M as Alp, and M equals what? M equals, consider about there, Alp X. Let's say this distance is X, and Alp X minus MO, that's it. MO minus Alp X, that's the moment. Okay, now let's plot the conclusion, this kind of conclusion, both conclusion. Oh, this one as well. Okay, when you consider shear force, in this range, RA minus QX is linearly decreased, and in this range, Alp is considered like this one here as well. Alp is considered. Okay, next the bending moment case. In this case, second order one, second order one. When x equals 0, second order one. And in this range is the first order, and here also first order increased, but some kind of a shift. This value was considered. Okay. Anyway, when you consider every case, then we can calculate shear force and bending moment. And finally, when you plot, then this kind of shear force and bending moment diagram. And when you consider bending moment diagram, this point is the maximum bending moment we can have. Okay. This kind of maximum bending moment is considered later on to calculate stresses and displacement inside the beam. Okay, in this case, example, some special case example. At first, we found reactional failure, and we consider this range and this range, shear force and bending moment we calculated. And finally, based on the values relationships, then we plot there, and finally we can find shear force and bending moment diagram. Okay, that's the 4 example special cases.